afternoon is going to be served by Dan Paraschiv from Bucharest, from the Institute of Mathematics of Romanian Academy of Sciences. The title is Achievable Connectivities for a Family of Singular Perturbations.
Hello, everyone. First of all, I would like to thank the organizers for allowing me to give this talk at this conference. Today, I will present a work that I did during my PhD at the University of Barcelona, together with my supervisor, Jarque and Rocha. I will start by introducing a very simple family with easy to understand dynamics and trivial geometry of the Julia set. To this, we will add the perturbation at the superattracting fixed point z equal to 0, which will increase the degree of our map and lead to much richer dynamics. Now, for this family, we will prove the existence of arbitrarily large finite connectivity path components in the dynamical plane, and we will specifically compute each achievable connectivity. So the setting of today is going to be the setting of rational maps. So we'll talk about a lot about the Riemann sphere. Of course, the set of holomorphic maps on the Riemann sphere is precisely the set of rational maps, which are always of this form. And in this talk, when we will use the notation Rn, we'll always refer to the nth iterate of the map R. As probably everybody in this room knows, we can divide the dynamical plane into two sets, the Fatu set and the Julia set, depending on whether or not the set of iterations of the map is normal in a neighborhood of the point or not. Now, a connected component of the Fatu set is called the Fatu component. A Fatu component is periodic if it eventually maps onto itself, and the Fatu component is called pre-periodic if it eventually maps onto such a periodic Fatu component. One of the first well-known modern results in complex dynamics is, of course, Sullivan's celebrated no-wandering domains theorem, which states that rational maps have no wandering domains. That is, any Fatu component of a rational map is pre-periodic. One of the main topics of today is going to be the connectivity of Fatu components, and by the definition of the connectivity of a domain is the number of connected components of its boundaries. Now, periodic Fatu component can be of four types. They can be part of attracting cycles or of parabolic cycles, and they can have connectivity 1 or infinity. They can be Siegel disks, which have connectivity 1, or they can be Hermann rings, which have connectivity 2. So we have that all periodic Fatu components can have connectivity 1, 2, or infinity. However, for pre-periodic Fatu components, we can have finite connectivities which are greater than 2. The first to prove the existence of rational maps with the first to prove the existence of rational maps with Fatu components of finite connectivity greater than 2 were Baker, Cotus, and Liu, which by means of quasiconformal surgery have constructed maps whose dynamical plane contain Fatu components of any given connectivity. They were doing this, of course, by increasing the number of critical points in the plane. It also must be mentioned that Kiao and Gao in 2004, using an idea given by Shishikura, were the first to construct Fatu components of connectivity larger than 2 in a specific map. That is, they constructed a rational map of degree 5, and they constructed Fatu components of connectivity 3 and 5. Later, Stimmer was the first to provide the specific family of rational maps for which he could provide Fatu components of any given connectivity. And finally, Canella in 2018 proved the existence of rational maps whose dynamical plane contains Fatu components of arbitrarily yet finite large connectivity. Now, I'm going to talk about singular perturbation. So the idea of singular perturbation is, once again, you start with some very basic map, for example, z to the power of n. You add a perturbation, for usually at a superattracting fixed point, and you get much more complicated dynamic. The first one to study singular perturbation was McMullen. McMullen intended to study and to prove the existence of buried components, components of the Julia set which do not lie on the boundary of Fatu component. And to do this, he studied the family z to the power of 2 plus lambda over z to the power of 3. Of course, now we talk about the more general case, z to the power of 10 plus lambda over z to the power of d. And he has proven that for modulus of lambda small enough, the Julia set is a Cantor set of quasi-circles. Imagine through a Cantor set, drawing one quasi-circle such that each of one of them surrounds the others. Then the next big result for us will be by Devani, Luke, and Uminsky, which had the so-called trichotomy theorem, where for the same family of rational maps, depending on the fact that the orbits of all the critical orbits iterate towards z equal to infinity, there exist three possibilities for the Julia set. The first one is the classic Cantor set. The second one is a Cantor set of quasi-circle, like in the Macmillan example, or a Sierpinski curve. A Sierpinski curve is a set which is homomorphic to the Sierpinski carpet fractal, like Cantor set in 2 dimensions. However, I have to point out that despite having a lot of Sierpinski curves in this family, the corresponding maps on their Julia sets, they are not necessarily conjugated. There were many other results on singular perturbations. For example, Blanchard, Devani, Garijo, and Russell studied perturbations due to the map z to the power of n plus c. Q, Roesch, Wang, Yin studied more the family of Macmillan. Morabito and Devani studied the family z to the power of n plus lambda over z. So we can see that this is a well-studied area. In here, we have some example of maps in the family z to the power of n plus lambda over z to the power of d. On the left, we have a Cantor set of quasi-circles. We can see all the quasi-circles surrounding each other. On the right, we have a Sierpinski curve. And I want to point out to you just that the lambdas are very small. We are making small perturbations which have a very large impact in the neighborhood. But for example, close to infinity, they have no relevance. Now, Jordi Canella in 2017 studied the family of generalized Blaschke products and added a perturbation to them. In there, he found that there exist parameters lambda such that the Julia set contains a countable union of Cantor sets of quasi-circles. So a countable union of such sets and uncountably many point components. In fact, these uncountably many point components together are homomorphic to a Cantor set. He also has proven that in this family, in the perturbation family, there exist parameters lambda such that the corresponding dynamical plane contains Fatu components of arbitrarily large finite connectivity. This is an example of a map from this family. I just want to point out to you at the moment that there exists these doubly connected components, which you'll see plays a key role later, and especially this triply connected Fatu component. As you can see, there are increasingly large connectivity Fatu components as we approach the boundary of the immediate basin of attraction of infinity. Now, I will talk about our set. So the family that we are going to talk about today is z to the power of n multiplied by z minus a over q, such that z equal to 0 is the superattracting fixed point of degree n. Q is a polynomial of degree at most n, with q of 0 different from 0, and z equal to infinity is attracting. So we have two Fatu components, which we can use another result to prove that they are separated by quasi-circles. And these Fatu components are precisely the immediate basis of attraction of z equal to 0 and infinity, each containing n critical points. The basin of 0 contains no other critical points other than itself, but it contains the point z equal to a as a 0. To this map, we add the perturbation at the superattractive fixed point z equal to 0. And we also add the somewhat necessary Macmillan condition 1 over n plus 1 over d is smaller than 1. Let's see some example of maps in our family. So on the left, we have a dynamical plane from the family z squared multiplied by z minus a, first studied by John Milnor and later on by Pascal Roche. On the right, we have very small perturbations to the map on the left. Once again, I want to point out to you this triply connected Fatou component. In here, we have more examples of maps from this family. Once again, the triply connected Fatou component. And in here, I want to point out that if we increase n, then it becomes very fast, very difficult to observe, let's say, the multiple connectivity. So here we use at most n equal to 6 in our examples. I'm going to now give a first rendition of the dynamical plane of the perturbation map, which is in fact a skeleton similar to many other perturbation maps. So first of all, we prove that infinity is we have that infinity is a superattracting fixed point, and it lies, of course, in its immediate basin of attraction of infinity. By using families of polynomial-like maps and J stability, we can show that the boundary of the immediate basin exists. I mean that the immediate basin of attraction is bounded by a quasi-circle. And so it is separated by this quasi-circle from its other preimage, z equal to 0. So once again, this is a map of degree n plus d plus 1. It has 2n plus 2d critical points. Infinity maps in the immediate basin of attraction of infinity. There are the n continuous extensions which come from the original map, and the point 0 maps, of course, with degree d, because our perturbation is plus lambda over z to the power of d. So d has multiplicity d minus 1 as a critical point. Now, of course, d, the point 0, lies in a Fatou component. Usually for perturbation maps, this Fatou component is called the trapdoor. Since we have that the basin of attraction of infinity is mapped to itself with degree n plus 1, and the trapdoor maps with degree d to the immediate basin, we have that there exists no other preimages of the immediate basin. We can also prove, just by using computations, that there exist n plus d critical points and n plus d preimages of z equal to 0, which lie in an annulus which surrounds the trapdoor. We also prove that these critical points and preimages of z equal to 0 all lie in one Fatou component, which we will denote by a lambda. This Fatou component a lambda maps with degree n plus d to the trapdoor. Now, since the degree of the map is n plus d plus 1, there remains one preimage of z equal to 0, which has not been found until now. And we will say that it lies in a simply connected Fatou component called d lambda. Now, until now, we have mentioned n plus d plus d minus 1 plus n critical points. There remains one critical point, which is free, and is the one which is in fact governing the entire dynamics of this family. So this family, after the perturbation, despite having degree n plus d plus 1, it is a unicritical family. So we can very easily study it in one parameter plane. Now, to be able to talk about connectivities, of course, we have to introduce the Riemann-Hurwitz formula. For U and V, two connected domains of connectivity mu and V, and f from u to v of degree d with r critical points, we have that mu minus 2 is equal to d multiplied by mv minus 2 plus r. We'll use this formula several times to be able to construct higher connectivities. I can point out to you now, for example, that if V is a disk and contains at most a critical point, then for certain U is also a disk. Also, if V is an annulus, so it has connectivity 2, and its preimage contains no critical point, of course, U also contains no critical points. So this leads us to the following observation. Assume that nu lambda iterates towards infinity. So nu lambda has to lie in a preimage of eventual preimage of the image basin of attraction of infinity, which cannot be any of the Fatu components that we have described until now. So it has to eventually, its image has to eventually pass through T lambda, and eventually its image has to pass through either D lambda or A lambda. If the free critical point iterates through D lambda, then D lambda and all its perimages, by what I have described before, have to be disc. So all Fatu components will be either disc or annuli. Now, if nu lambda lies in an eventual preimage of A lambda, then all the eventual preimages of A lambda, except for the one containing the critical point, have connectivity equal to 2. However, if we have the critical point in an eventual preimage of A lambda, so we have that V would be an annulus, but R is equal to 1, we get that the Fatu component containing the free critical point will have connectivity equal to 3. So now we have the following lemma: assume that the free critical point lies in a Fatu component which is eventually mapped onto A lambda and surrounds Z equal to 0. Then this Fatu component is triply connected and it lies in the exterior annulus. So it lies in the annulus bounded by L lambda and the image basis of attraction of infinity. Let me now state theorem A. So let our perturbation map satisfying all the previously described conditions, and modulus of lambda is small enough. Assume that the free critical point lies in a triply connected Fatu component which surrounds Z equal to 0. Now let K be the minimal number of iterations needed by the free critical point to be mapped into the region bounded field by the annulus A lambda. Then, if U is a Fatu component of connectivity kappa, there exists IJL such that this is the form of any connectivity of a Fatu component in the dynamical plane, with the added condition L smaller or equal than J times K. So now we get even more insight into the dynamical plane. Recall that we had our immediate basin, we had the trapdoor, and we had the annulus A lambda, which contained n plus d critical points and free image of Z equal to 0, which lies in the annulus bounded by the immediate basin and T lambda. First of all, we have this region called UD, which maps, UD is the region bounded by T lambda and A lambda, and it maps to the region bounded by the immediate basin and the trapdoor. So every Fatu component in the annulus on the right has a preimage which maps to it with the grid D in the red annulus on the left. Now, we come back to our triply connected Fatu component. So this triply connected Fatu component has, as we have talked before, it has an image which is an annulus, and it lies in the region bounded by U sub nu, the triply connected Fatu component, and the trapdoor T lambda. Now, the region bounded by the immediate basin and the triply connected Fatu component will map with degree m+1. And in fact, we can also prove that any Fatu component which lies in the region Vm+1 has a corresponding preimage in the region Um+1, which maps to it with degree m+1. So if you recall the Riemann-Hurwitz, this will allow us to increase the exponent of the m+1 coefficient. Similarly, for the region Vn, bounded by the image of the triply connected Fatu component containing the free critical point and the trapdoor, there exists for any Fatu component in this region Vn, there exists a Fatu component in Un, which maps to it with degree n. And in the last, in the region bounded by the last boundary component of the triply connected Fatu component, the one which also contains the preimage of Z equal to 0, we have also preimages of which map with degree 1 to the Fatu components in Vn. Now theorems B and C. Theorems B states, okay, so you previously have given me the general form for all possible Fatu components. Now, but can you attain all of these connectivities? Theorem B says that if you have the condition L times L smaller or equal than J times K minus 1, unlike before where we had L smaller or equal than J times K, then yes, I can prove you the existence of such a Fatu component of connectivity m+1 to the power of ID to the power of J and to the power of L+2. And theorem C says, okay, have you have talked about some random theorems about some possible Fatu components which may exist or not. But theorem comes and says, yes, all of these Fatu components, they exist. If you give me any I, Lj, then I can give you Fatu components of connectivity m plus 1 to the power of I, d to the power of j, and to the power of L plus 2, and Fatu components of this whole. Finally, I want to discuss a bit about the parameter plane of this family. So I want you to remark that on the left, we have lambda of the order 10 to the power of minus 5. On the right, we have lambda the power of 10 minus 12. Now, it seems obvious that if we have a perturbation, we will get this type of images. And the more we zoom in, the more we'll find the same thing. But in fact, we were not able to prove much more about the parameter plane rather than theorem C. So there is much to be seen. Thank you very much.
Questions from the audience here?
I have a request. Could you go back to slides? Because the slide. Go back to slides. Another one, 2 slides. 1 and 2. Thank you. I do have a question. So can you take this sets for any given I? So this doesn't mean that you can have a map which has two components of basically every single connectivity. Am I reading this last sentence right?
This one? Yes, this is really trivial to obtain. In fact, you get the triply connected Fatu component, and you just take its preimages in the annulus UM plus 1. And as you approach the boundary of the immediate basin of attraction of infinity, you take 10 preimages, you get n plus 1 to the power of 10.
That's not. No, those combinations are not gonna run through all the natural numbers, right?
Again?
Like those combinations are not gonna cover all the natural numbers, right? So you're gonna have some gaps.
Of course, they are not all the natural numbers. They are all the natural numbers of this form.
But have any Fatu components with those connectivities?
You can just choose my own n and d and so on. If I want a specific number, I can just choose two of its divisors, and I can make it of this form.
No, but like if I fix a map, like
Is this theorem
I fix then and G and lambda. So in that dynamical plane, I'm only gonna find certain connectivities, right?
You have arbitrary large connectivities. You can just keep taking connectivities, and keep taking preimages, and you increase these coefficients as much as you want.
Well, I tried to ask the question. So the question still is okay. So we have a fixed set of components with connectivity. Do we know that that do not exist the other the components with other number of connectivity?
Yeah.
I think I'm trying to ask the same question.
Yeah.
The restriction that you are asking about, is it this one, or you mean like, for example, m plus 2? Because I can guarantee to you that in here there is no component of connectivity m plus 2.
Okay, so you know that some of those components do not exist.
I know for certain that all the Fatu components of this type exist. I know that they are limited by this condition. In fact, this condition is much, how should I say, much less restrictive than it appears, because in practice you get all the Fatu components, including up to L equal to J times K. However, for the very bad case where you have, if you have, for example, the use of nu would map directly into the annulus, in the interior of the annulus UD, and from there it would instantly map outside in this annulus. That's the only case where you cannot get all the results in theorem A. But otherwise, you get theorem A says that any Fatu from component from the dynamical plane has a connectivity of precisely of this type.
So I have a related question. Is there a map for which you know that for every n there exists a component of connectivity n?
Yes.
You're asking me if I know that for any n there is fat components of connectivity n.
No. Does there exist one single map?
Which has two components of every single connectivity.
Yeah.
Wow, this is, I don't know this. I mean, this is a much more complicated question rather than my problem.
Any other questions? And online audience, please ask a question. Do you want to ask a question? Online audience. How do we know?
One.
How do we know?
Otherwise, internet will be turned on.
So probably not. If not, then thanks, done Paraschiv again.
Sure.
The session.